I'm going to begin today's presentation by talking a little bit about UK CP18, the latest set of climate projections produced by the Met Office. I will talk through some headline results in the context of the UK water industry, and then move on to the so what. So it's all well and good knowing understanding how summers will likely change in the future, but what does this actually mean, and how are we going to work with the UK water industry to help them prepare for those changes and to become more resilient. I'll then give a couple of quick examples of the types of projects we work on, and in the process show you that not everything we do is about UK CP18. We also use lots of other data sets and novel science to answer a whole range of industry problems. But first, starting with UK CP18. So what is UK CP18? Well, it stands for UK Climate Projections 2018. And it is a major upgrade on UK CP09, which, as the name suggests, was the previous set of climate projections released in 2009. The aim of UK CP18 is to serve as a major upgrade on the older UK CP09, reflecting recent advances in climate science. And it stands as the authoritative dataset to inform the third climate change risk assessment, which will be released in 2022. So in terms of the science, it represents rapid developments over the last decade or so, incorporating new climate models, the latest observations, and also very high resolution simulations. It uses the latest statistical thinking to inform a set of probabilistic projections and uses a lot of data from climate models. And we're able to run those models now thanks to having faster supercomputers, and obviously this will continue to improve over the coming years, which means we'll be able to run increasingly high resolution models with more processes simulated in them. The upgrade also reflects improved user input. It has been designed as a climate service involving users from the inception stage, and a series of stakeholder engagement events and co-design workshops were run to ensure that the end tools were suitable for a range of UK users, sectors, and industries. This schematic shows that early process of iteration and how the final projections were designed using that detailed input from end users. So the main set of projections was released in late 2018, but this has actually been added to with a further release or a further strand that was some very high resolution simulations released in late 2019. And more recently, we've released some extreme indices, as well as some widely used metrics representing phenomena such as the jet stream and the North Atlantic Oscillation. So what does UK CP18 tell us? Well, the key headline result is that the UK will face a greater chance of warmer, wetter winters and hotter, drier summers. This is a message that falls out of all of the UK CP18 strands across models of varying resolution, and it's even something that's been suggested in older, coarser resolution models. And in some sense, the message has remained largely unchanged since UK CP09. So it isn't particularly surprising that this headline message, it's just been reinforced by a wealth of additional science behind it. And as a general rule, the changes that we see, and in turn the impacts we see to the water sector, and indeed all sectors across the UK, are predicted to be amplified for higher levels of global mean warming. So in other words, some of the impacts felt by these changes will be avoided by limiting warming to, say, 1.5 degrees Celsius rather than 2 degrees Celsius. That's global mean warming rather than UK warming. So just giving an overview of UK CP18 and the projections that are available over land. There are 5 strands. 1 consists of the probabilistic projections, 3 consist of climate model projections at various spatial resolution, and there's also some derived projections. So the probabilistic projections use a combination of information from a number of climate models, from simple idealistic models to kind of complex coupled models, and combine these with a statistical methodology to attempt to sample the full range of potential future outcomes for the UK. In other words, they produce a full probabilistic range and represent our best estimate of the uncertainty in future UK climate. Then we move on to the climate models themselves. So we have some global projections, which consist of 28 models run at 60-kilometer resolution. And these are spatially and temporally coherent, and means that we can look at global impacts. So we can look around the world and understand how changes in one part of the world, perhaps in the tropics, might impact climate over the UK and Europe. Moving to higher resolution, 12-kilometer resolution, we have some regional projections, and this covers the European domain. And at that resolution, we can focus more on climate extremes, just because these models simulate some of the climate extremes, and particularly those extremes that have an impact on society in a better way than the coarser resolution models do. And then finally, we move on to the local projections, which are a set of models run at 2.2-kilometer resolution. This is typically a resolution more associated with day-to-day weather forecasts, and even just running those out 48 hours into the future takes quite a long time. So you can imagine how long it took to run these several decades out into the future. And that was part of the reason why these projections were released a year later than the other bulk of UK CP18 strands, just because it took so long to run them on our supercomputer. These are particularly good at understanding extreme short duration rainfall and wind gusts, again, because they represent a high resolution. They also more faithfully simulate some of these short duration extremes. We also have some derived projections which come from the global projections, and these allow for framing around levels of global mean warming. So for example, what does the UK climate look like in a 2 degrees Celsius warmer world and a 4 degrees Celsius warmer world? So I'll just go through some of the key headline findings now from UK CP18, focusing on those strands. Starting with the probabilistic projections. And this slide shows one of those key findings, and it shows the analysis of the summer 2018 heat wave. So hopefully that's still quite fresh in the memory. Summer 2018 was the joint hottest on record for the UK as a whole, and indeed the hottest for England. It put a lot of stress on a lot of sectors and infrastructure, but none more so than the water sector, where water companies across the UK were struggling to supply water during record water demand. But how rare was this event, and what might it look like in future? This is something that we can address using the probabilistic projections, and they show us that in the recent past, so at the end of the 20th century, the chance of seeing a summer as hot as 2018 was low, less than 10%. That chance has already increased due to climate change and is now about 10 to 25%, but with future warming by the middle part of the 21st century, hot summers could become even more common, close to 50%. Moving further on to the end of the 21st century, well, the types of summers we see then are quite scenario dependent. So if we manage to curb emissions, the summer 2018 will occur roughly 1 in every 2 summers. But under a high emission scenario where we haven't managed to mitigate emissions, these summers are more likely to be seen than not. So around about 80 to 90% of the time, which is quite alarming when you think back to how warm 2018 was. This analysis is from the global projections, so using the climate model output itself. And consistent with earlier projections, these models show an increased chance of warmer, wetter winters in the UK, with the trend towards wetter winters shown by the figure. This shows UK mean winter precipitation change across the 20th and 21st centuries, and the change is calculated relative to 1981 to 2000. Interestingly, variability in winter rainfall is also projected to increase. And what this means is that while winters will get wetter on average, we can still expect to see very dry winters, perhaps even drier winters than we're used to seeing. This means that the UK water industry will need to be resilient to a wider range of conditions than we are used to. This analysis is from the regional projections, so those simulations run at 12-kilometer resolution. And this is the spatial pattern of precipitation change across the UK by 2070 relative to the late 20th century in the high-end RCP 8.5 emission scenario. And this by 2070 corresponds roughly to about 3 degrees Celsius of global mean warming. The median estimate is shown with a red border and represents the outcome that is most likely to happen in these models. However, they should always be placed in the context of those probabilistic projections that I talked about previously. And on the left-hand side, we have the summer precipitation changes, and on the right, we have the winter precipitation changes. These plots reveal some of the spatial characteristics of this change. And at such high resolution, it's a spatial structure that we can generally believe in, since features such as orography will be better represented at this high resolution, and the interaction of rainfall with this orography is in turn also better represented. You can see here that the strongest drying is projected to occur in summer. It's projected to occur in the south and west of the UK in summer, and the strongest increases in rainfall are projected to occur across the south of the UK in winter. So this is some kind of meaningful and informative spatial detail to some of those headline messages that we saw before. And what this means is that we start to get a bit of an understanding of where water is going to be needed most by the end of the 21st century. And that means that water companies can prepare infrastructure accordingly. And for example, they might want to start planning to start transferring water from areas where it'll be more plentiful to areas where there'll be a need for water, as we see particularly drier summers by the end of the 21st century. Finally, this slide summarizes the key features of the projected rainfall changes from the local projections. So those are the very high resolution models. And these models better represent rainfall characteristics, especially very intense rainfall. And these plots show the projected changes in wet days, defined as days with more than 1 millimeter of rainfall, and also the projected changes in wet day intensity. Again, the red box represents the most likely or median estimate from these models. And the changes are shown again for summer in 2070 relative to the late 20th century. So what they show us, in other words, is how much it rains when it does rain. So we see that the frequency of rainfall days in summer is projected to decrease, but the intensity of rainfall on the days that it does rain is projected to increase. So what this means is we expect to see longer or lengthening dry periods in the summer, punctuated by very intense downpours, more intense downpours than what we expected, than what we're used to seeing in today's climate. Also, we find from these local projections that for the most intense events, so the maximum hourly precipitation seen in a 2-year period, the central estimate is for an increase of 25% by 2070. So this means that our most intense events will become more intense by around 25%. So this is critical for understanding how vulnerable key water industry assets and infrastructure might be to flooding as we move towards the end of the 21st century, and allows us to sort of make decisions or long-term planning decisions around some of the infrastructure that is built and planned today. So while we have concentrated entirely on land projections so far, there are also marine projections in UK CP18. And in one sense, the marine projections are quite straightforward. Sea level rise will occur for all emission scenarios and at all locations around the UK. The sea level rise will be greatest in the south, and while there is no clear signal for a change in storm surges, when they do happen, they will occur against a backdrop of rising average sea level. Therefore, that means that they'll have a more significant impact and more coastal infrastructure will flood if everything else remains constant. So we don't improve our seawalls and we continue to build infrastructure by vulnerable coastal locations. Those assets and that infrastructure will flood more regularly if nothing else changes. So what we're seeing so far represents the key headlines from UK CP18, but how do we actually apply this data? How do we translate that science into industry solutions? This slide and the next slide show a sample of real questions that we've been asked by UK industry and gives a very simple taster of what UK CP18 products we might use to answer those questions. So, for example, we've been asked, how common will hot and dry summers like 2018 be by 2050? And this is particularly important because future demand has to be set against a backdrop of requiring extra water capacity for public water supply. This is required to make water supplies more resilient to drought, to supply an anticipated growing population, and also to replace unsustainable abstractions and to generally improve the environment. For this, the global projections would be a good tool to use because they allow for spatially and temporally coherent projections of UK climate and also sample quite a large range of potential future outcomes as well. So they are well suited to answering that question. Our sewer was flooded after 50 millimeters of rainfall in one day. How often will this occur in 25 to 50 years' time? Well, for this particular question, the regional and local models are suitable because they have a better representation of such intense rainfall. Although, because they are particularly partially limited in their number, there could be scope for combining that information with other statistical techniques, such as extreme value analysis. And this is something we typically do to answer questions around extreme rainfall and how that might change into the future. What could an extreme 6-month rainfall deficit look like by 2070? And this is something we typically get asked in response to water resource management plans. And for this particular question, global and regional models combined would probably be a good way forward. But you'd want to supplement that information with the probabilistic projections as well. And these help to constrain the changes that are indicated by the models. So you can see answering these questions, there's a sort of combination of tools and a combination of UK CP18 strands that you might want to lean on depending on the question at hand. Moving on a little bit more, and as I said, these are just a sample of some of the questions that we get asked. So another one that has come through to us recently regards sewer flooding, and we know that UK water companies often struggle with sewer flooding when we have intense rainfall at the end of long dry periods, and they want to know whether this risk will change moving forward. Well, of course, this sort of relates to that projection of seeing lengthening dry spells punctuated by intense rainfall as we move further into the 21st century in the summer months. So we've got quite a clear signal for this kind of thing happening. And unfortunately, that means that our sewers, without any changes, will probably become more susceptible to that type of flooding. And for this, the regional and local models, again, are particularly useful for understanding this question because they represent these intense rainfall and the dry periods that go between these intense rainfall better than some of the other UK CP18 strands that we have. We've thought quite a lot about warm weather and intense rainfall so far, but of course leakage that occurs during freezing weather is also important because that causes a spike in demand. So how will freezing days change in the future? And this is something that we often get answered and has particularly come into focus with a couple of recent events over the last decade. So the Beast from the East event in March 2018, and that particularly cold December we had exactly 10 years ago in 2010. And both of these events led to significant disruption to the UK water industry, and the UK CP18 regional projections and regional models, given their high resolution and their ability to represent orography and the sort of the spatial variability that we expect to see from cold weather events, would be well suited to answering this question. Another more recent question we got at the start of this year in the summer was around the swing from this year's very, very wet winter to very dry spring. So while that dry spring was nice for a lot of us who got to spend a bit more time in the garden than we were perhaps expecting. It did cause the water industry a lot of headaches, particularly as we were sort of using water in quite unusual ways, with many of us being at home. So is this swing in weather quite unusual between seasons? So we could look to UK CP18, particularly the global and regional models, to answer this question, but can we actually do better? And this kind of goes back to the point that UK CP18 is a wonderful resource, but we also need to sometimes supplement that with other statistical models and even other data sets as well. And this is something that I'll lead on to next, just by giving a little bit of a flavour of some of the projects we work on and how we look at data outside of UK CP18 and some of our in-house kind of expertise to actually answer some of these questions in a better way. So this all relates to meeting industry needs, and as I said, it isn't exclusively about using UK CP18. There's often a situation that requires, there isn't often a situation that requires a single data set and taking the direct output from models. We sometimes have to combine multiple novel data sets with our world-leading expertise in science. The data sets that we use are typically supplemented by mathematical or statistical models developed by our expert scientists and consultants. And these allow us to establish a robust link between weather and climate and industry exposure. And we often work closely with an organization to really understand their exposure to a hazard. Answering industry questions typically comes down to the issue of working around limited observation data. So even though here in the UK, we're in somewhat of an enviable position in that we have long observed records with, say, 150 years plus of rainfall records, it is still quite difficult to calculate with confidence what the potential, say, maximum 36-month rainfall deficit looks like. We simply haven't seen enough of these extreme events to really quantify that to a degree of accuracy. We can use extreme value analysis techniques to fit to extreme values in time series, but this also has some limitations and uncertainties when we don't have an optimum sample size. So as you can see, a lot of these questions come around the need for kind of more data, and UK CP18 can partially supplement that, certainly better than older climate projections produced by the UK. But sometimes we have to look to other data sets as well. And we can use these pseudo observations that come from a climate model, otherwise known as hindcasts. And we can also use statistical models to generate alternative, say, rainfall time series as well, which then informs our drought risk over a longer period of time. And I'll just talk around these two examples, and these relate particularly to two projects that we've been working on in our team recently. So using pseudo observations from a climate model. So this relates to a technique known as unseen, which stands for unprecedented simulated extremes using ensembles. And it's a technique that's been developed recently within the Met Office using hindcast simulations to test the full range of potential alternative observations. So really it's around the question of how often will we see something at least as bad or worse than what we've seen so far in the observed period. And we use what's known as a decadal prediction system model to answer this question. And this consists of 12-month chunks of simulations or hindcasts or retrospective forecasts for each year from 1959 up to the present. And for each of those 12-month simulations, we run the model a total of 40 times. And what this does is it bypasses the need for statistical methods by creating plausible alternative observations. In other words, we have 40 times more data than is available from observations alone. And what this means is it's capable of sampling more extreme cases than in the available observations. So in other words, it allows for the identification of unprecedented or unseen events. As I mentioned, this has been developed across the Met Office in recent years, and it can be applied to a number of problems that are of relevance to the UK water industry. For example, it can be applied to understand winter flooding. If you remember back to the winter of 2013-2014, we had a very wet period of weather that was associated with a number of storms that came through. and led to significant disruption across the UK. That was the winter where the railway track was left suspended across the sea down here in Devon. In January 2014, Southeast England experienced unprecedented rainfall, the highest monthly rainfall on record for that region. What this paper here wanted to do was ask how unprecedented was that rainfall seen in that month, and we can answer this using the unseen method. So this paper was able to robustly quantify that in Southeast England, there is a 7% chance of exceeding this current rainfall record in at least 1 month in any given winter. Therefore, what we essentially showed was that rainfall total in January 2014 wasn't entirely unprecedented, and we also quantified what the most extreme winter rainfall month could look like in today's climate. So the model produced some very high monthly rainfall totals above and beyond anything that has been seen to date, but shouldn't be viewed as unprecedented. This technique has also been applied to that recurring issue of the summer of 2018, and the unseen method can be used to determine the likelihood of a summer 2018 event happening in today's climate. And it suggests that the likelihood is around 10 to 15%. This is in excellent agreement with the likelihood determined from UK CP18 probabilistic projections, if you can remember back to that previous plot that I showed you, and that suggested that in today's climate, the likelihood of a summer 2018 type event was around 10 to 25%. So we've shown applications of this unseen method to winter flooding and also to hot summers as well. But we've recently extended it to support a UK water company and applying that technique to drought, specifically to understand the likelihood of seeing extreme 36-month rainfall deficits in today's climate, and also understanding what the worst case deficit could be today as well. Before quantifying the chance of such events, an important first step is validating the model to ensure that it faithfully represents observed characteristics of drought and drought variability. So this model validation is applied to all applications of the unseen technique. So essentially you want to be sure that your model is capable of faithfully representing the observations before you trust what it's given you in terms of an indication likelihood of exceeding, say, certain thresholds, for example. So this validation step is a really important one in actually having confidence in the model and what it's telling you. Here, in the context of drought, we show that the model, represented by the red dots, is indistinguishable from the observations shown by the blue dots when considering a number of drought metrics: magnitude, duration, and severity. Therefore, we have confidence that the model can faithfully represent long duration drought, and this right-hand plot shows some of the outputs and what we determined from applying this technique. It shows that the most extreme observed 36-month rainfall deficit experienced in this region was around 400 millimeters, but the unseen technique shows us that it could be as severe as 600 millimeters even in today's climate, which is quite an alarming result in some sense. We haven't seen that event yet, we haven't observed it, but this model suggests that it isn't out of the question. A second technique that goes above and beyond UK CP18 and that we've been applying, working with a UK water company in recent months, surrounds statistical models and using them to generate alternative time series. So this again gets around this question of generating more data where it's needed most. So to help generate more data statistically, we have come up with a statistical framework known as the Advanced Meteorology Explorer, or AIM. And as I said, this has been developed working with UK water companies to help them understand the full range of plausible drought events in their region, and that helps them to inform future infrastructure planning. And one method for producing these drought events is to stochastically simulate rainfall from a statistical model. And this is something that's been done by the industry, working with UK water companies over the last decade or so. And this stochastically simulated rainfall can then be run through the water company's hydrological models to explore downstream impacts. So we've been motivated to develop this model and to improve on previous stochastic simulations for a number of reasons, just because there are a number of limitations around current approaches. They typically only simulate at monthly temporal resolution, whereas the water companies require daily temporal resolution. And these outputs often require bias correction to represent the most extreme observed droughts, which isn't ideal to be doing before you actually use them offline in hydrological models. And also, they've only been extended to future periods in a very simplistic sense. So to represent climate change, there's been a simple scaling factor applied to existing droughts to understand how they might change in a warmer world. We've kind of extended that using this advanced meteorology explorer by simulating daily rainfall as is required by the hydrological models. And in this particular application of the AIM model, we've simulated rainfall for 39 sites in a region using the AIM model, which is based on a Bayesian statistical framework. And we ensure that the rainfall simulations are coherent in space and time before we extend to a high resolution 5-kilometer grid covering the region. In total, we produce 1,000 we produce 1,000 alternative gridded simulations for the region, which sample a wider range of outcomes than are available from observations alone. And the rainfall in these simulations also varies with climate drivers such as the North Atlantic Oscillation, known as the NAO, using the statistical relationship between these drivers and rainfall. It has also been extended to include the effects of future climate change, incorporating information from UK CP18 climate models. So while this doesn't rely on UK CP18 in its setup, we still use that really valuable information from UK CP18 climate models to inform the future stochastics that we are generating. And generally, this validates really promising, and the outputs from this have been highly encouraging. We've managed to produce alternative plausible realizations over the historical period and up to the present day. And as I said, we're currently applying this to the future period. So this plot shows the drought simulated by the model using what is known as the deficit drought index to represent drought. The blue line shows the observed variability and the black line shows the average of the simulations, with the gray lines showing all 1,000 simulations separately. So this model is capable of capturing the observed variability and particularly some well-known drought events shown by the positive values here. While also simulating more extreme dry and wet periods than was seen in observation. So it pushes the bounds of the extremes at the high values. And this again gives the water industry an idea of what the worst case scenario in today's climate might be, and what they already need to be resilient to. And as I said, we're extending that to the future period to understand that as well. So hopefully that gives you a sample of some of the, an example of some of the work we're doing with the UK water industry that goes beyond UK CP18 to really help them understand, in this case, what I've shown you, changes in future drought, changes in present day and future drought, and potentially the worst case scenario that we could see in today's climate. So that's everything I've got to talk about today. Thank you very much for listening.